So how do we initialize this? It turns out that there's something special needs to be done for the bisection method. There are two conditions. One is you need to give it two guesses, two numbers. Needs and the second condition is that those two guesses have to bracket the root. Can I explain what that means? So f of x is the function whose root I'm trying to compute. Clearly, that solution is right here. That's when f of x intersects the x-axis. Okay, let's call those two guesses as x1 and x2. Okay. So those the two guesses should bracket the root. What that means is I need to choose those such that the solution is between x1 and x2. Okay, so I've done it that way. So if you choose x1 here, x2 here, that will not work. Okay, because that's how like you see the once I go to the search direction, it will be more obvious. So how do we know if we have bracketed the root? It's obvious what it means to bracket the root from the figure. It means that f of x1, which is this point, and f of x2, which is this point, should be of different sign, right? F of x1 is positive, f of x2 is negative. Okay, so that's what it means to be bracketing the root. So this condition is that f of x1 times f of x2 should be less than 0. Okay. So that's a must. If you don't have that, bisection method will not work. In fact, in the code, we'll actually check this. If you don't give an initial guess which doesn't bracket the root, we're going to reject the initial guess and say we cannot proceed. So you need to do that check before you apply bisection method. Okay, the next we go is the search direction. What the search direction means is from x1, x2, we need to now zone in and get to the point where f of x equals 0. So how do we go from x1, x2 to a different point or set of points such that they are closer to f of x equals 0? Okay, so let me do the construction. It'll be more obvious this way, and then we'll develop the logic. So let me take this figure. Okay, so what bisection method will do is that your next guess, let's call that x3, is going to be the arithmetic mean of x1 and x2. Okay. Okay, so where would that lie? Well, it seems like it's over here. Okay, let me just move this so it's become more obvious. Okay. Yeah, so that's approximately midway between x1 and x2. Okay, we can also find or compute what f of x3 is. It's basically this point. Okay, so this is what is the bisection. This is why the method gets its name. It's basically bisecting the 2 points. Okay, now what we'll do is we'll again try to find which two values bracket the roots with x3. So x3 is a new point. We're going to find if x1 brackets the root, we'll keep x1. If x2 brackets the root, we'll keep x2. So it's clear that x3 and x2 bracket the roots, right? The root is between x3 and x2. So we discard x1 and we keep x2. So now new two guesses for the next iteration is x3 and x2, because x3 and x2 bracket the root and x3 is closer than x1. Okay, so that is how you would do it using this graph, but we want to do it numerically. The computer code will not understand a graph, right? So how will we do that? Well, what we do here is we check for the product of f of x3 and f of x1 or f of x2, whatever you wish. So if f of x3, that's the new point, times f of x1, that's one of the 2 points, doesn't matter which one, is less than 0, right? This is, by the way, this is just a check I'm doing, right? This is something which I'll implement the code. If that's true, right? If 2 points are, if the solution is between x1 and x3, then that condition will be true. That is precisely the condition that the root is bracketed between x1 and x3. If that is true, then what we do is we found a new, the new bracket is x1 and x3. So what we'll do is we'll discard x2 and keep x3. So x2 is discarded. Else we know that the other condition will be true, which is f of x2 times f of x1 is true. So else we would basically discard x1. So discard x1 and keep x2. So now the new bracket. So let me just put it here. So what this implies is basically a new bracketed root is x1, x3, and this means the new bracketed root is x2, x3. Okay, so this is just something we'll do to check this condition here. If you apply it right here for this figure, you see that f of x1 times f of x3, this condition is untrue, right? Because f of x3 is positive, f of x1 is positive. So the multiplication is greater than 0, which means you do not apply this condition. You'll actually apply the other condition, which is it's not true. So what you'll do is, this one is saying you're going to replace x1 with x3. So you're basically discarding this and you're keeping this. So when you keep this point already exists. So this is the new bracket. So we found x2 and x3 as the new bracket. And then we apply the same method again, which is we take the bisection. So we take the mean, apply the same logic, and just keep doing that till we hit the solution. Okay, so this is the, depending on which one, that's the condition. And the final step is the termination. So there are two things we'll do. We'll check if absolute value of x, it could be anything. It could be x1, x2, x3, whichever. Let's say x3. If it's less than epsilon, and you can give whatever value you want, so possibly a small value, then you just say stop. Or the other thing you could do is so this step of computing x3 is one iteration. You do that a second time, a third time, fourth time. If the iteration count becomes greater than the max iteration, there's something which you specify. Then also you can stop. Okay. So that's all to it. It's the three things. Okay, when we code it, we'll do all those three things. Okay, so what I'll do is we'll do a hand calculation to see that we understand this algorithm, and then I'll write a Octave code to be able to do it. So using bisection method, compute the root of the equation f of x equals x squared minus 3x use 1, 4 as the initial guess, and then Okay. To up to 3 iterations by hand and up to a tolerance of 1e negative 3 using Octave. Okay, so turns out that it requires much more than 3 iterations to terminate, and I don't want you to spend your time doing these calculations, which can be done by computer. But nevertheless, we need this to do it by hand because that's what will be tested in the exam. So we'll do 3 iterations by using hand calculations. We'll write a computer code and do many more iterations. In fact, we'll do it till 1e negative 3, and then we'll compare the answers. Okay, so first of all, for this example, it's always good to, when you write a code, a new code, it's always good to try out simple problems whose solutions you know. That way, when you do the testing, you know the solution and you know your code is working, and then you can do examples which are much harder. So in this case, we kind of know what the solution is, right? What's the solution for this equation? What's the root of x squared minus 3x? 0 and 3, right? If you put f of x equals 0, you get f of 0 is 0. See that? And if you put x equals 3, you get f of 3 is the 3 squared minus 3 times 3 is 9. 9 minus 9 is 0. So we know that the solution is okay. Okay, so here we go. So iteration 1. Okay, let's choose x1 is 1, x2 is 4. Okay, let's compute f of x1. So we just literally put it in the function. So 1 square minus 3 times 1 is minus 2. F of x2 is 4 square minus 3 times 4 equals 4. Okay. So the next step is to compute x3. That would be the arithmetic mean of x1, x2. So that would be 4 plus 1 divided by 2. That's 2.5. Okay. We also need to compute f of x3, which is going to be 2.5 square minus 3 times 2.5. And this comes out to be negative 1.25. So the work we did was to compute f of x3, f of x1, and then f of x2. Okay, so that is, we're setting up for the search direction. So what we said was we need to check these conditions. If f of x3 times f of x1 is less than 0, then x2 equals x3. Otherwise, x1 equals x3. So let's just do this check. So the check we have is f of x3 times f of x1 equals minus 1.25 times f of x1 is here minus 2. So this is, you don't have to do the multiplication. It's just positive, right? It's greater than 0. Okay, so that condition is not met. But if you check f of x2 times f of x1, you see that you get 4 times minus 2, which is less than 0. That means that the new root is bracketed between these two. So x1 and x2 bracket the root. So what you need to do is you need to replace sorry, my bad. This should always check with the new one. My bad. F of x3 times f of x2. So f of x3 is minus 1.25 and f of x2 is 4. So which is less than 0. So the new root is bracketed in x2 and x3. Okay, so what we do is we replace a new x1 is x3 because we want to discard x1, right? X1 is discarded. Because it no longer brackets the root, which means that you discard whatever is discarded becomes the new guess. So we have x1 and x3. So the new root is now bracketed between x3, which is 2.5, and the second one is x2, which remains, so it's 4. So we've gone from 1 through 4, which is a difference of 3, right, to 2.5 to 4. So we are getting closer, right? Where the bracket is decreasing in size. That's what you'll see in bisection method. So we got that. Next, go to iteration 2. Okay, note we're starting with 2.5 and 4. So f of x1 is 2.5 square minus 3 times 2.5. And then f of x2 is 4 square minus 3 times 2, 3 times 4. That is minus 1.25. This is something we also, by the way, we computed that previously. I just want to write it here because it's on a new page. This is going to be 4. Next, we compute x3. That's x1 plus x2 divided by 2. That's going to be 2.5 plus 4 divided by 2, which is 3.25. Okay, so next we compute f of x3. So 3.25 square minus 3 times 3.25 comes out to be 0.8125. Okay, all you have to do is check the condition. Let's see what we have. We have negative, 4, and positive. Okay, so clearly we need to take the new solution and find that which one and f of x3 is less than 0. So clearly the one which is less than 0, if you take a product, it's going to be minus 2.5. So we note that f of x1 times f of x3 is minus 1.25 times 0.8125 is less than 0, which means that we have no use for x2, right? We need to discard x2. So what we do is we take x2 and we replace it with x3. So then our new root is bracketed between, so x1 remains as it is. So x1 is 2.5. And the new x2 is same as x3, which is 3.25. So again, we've shrunk the region. Okay, let's do one more iteration. Okay, last iteration. Okay, we have bracketed the root between 2.5 and 3.25, I think. Yeah. So we know that f of x1 is f of 2.5. Now, you don't really need to do this calculation. You've probably done that before. So I'm just going to write the value, which was negative 1.25. And then f of x2, which is f of 3.25. Again, something which we did. We did compute that value. So on the previous page, it came out to be 0.8125. Let's use the bisection rule. So that's 2.5 plus 3.25 divided by 2 comes out to be 2.875. And then f of x3 is 2.875 square minus 3 times 2.875. It's minus. Okay. Let's check the values of f of x. So we have a negative value, we have a positive value, we have a negative value. So just to check x1, x2, x3. Okay, so we notice that f of x3 is negative, and we just have to pair up with the one which is positive, which is this one. It means that x2 and x3 brackets the root. So we notice that f of x2, f of x3 is less than 0. That means we have no need to keep using x1. x1 can be discarded. So if you discard x1, then the new x1 will be x3. Okay, so the new bracketed solution is going to be x1, which is x3 is 2.875, and x2, which is untouched, 3.25. Okay, so yeah, so let's see where we've gone from. So we've started off with so for this example, we started off with 1 and 4. So the gap is 3, right? And then we went to iteration 2. We reduced it to 2.5 to 3.25. So that gap has decreased from 3 to almost 1.25. And then when you go further, iteration 3, it's reduced further. Right? So it's getting closer and closer. We know that the solution is 3. And so in 3 iterations, we're pretty close. Okay, now we don't want to keep doing that. So let's just write code which will do this till it converges to whatever tolerance we set. Okay. Okay, so when I took this course as an undergrad, I wrote code myself, but let's just use ChatGPT because it's much easier to. I mean, it's fine if you use ChatGPT because that's a new tool, and I think it's inevitable that you'll use it for your work. So what I'm going to do is, as I told you, every time you talk with ChatGPT, it remembers the conversation. So we had this sort of chat where we did forward difference. And I would recommend that each time you do a new thing, start a new thread. So we can start a new chat. Here we have a very specific example. It's essentially the same problem. We just ask the same question and see what it gives. So write Octave code to solve for the root of x square minus 3x using bisection method and an initial guess of 1, 4, terminate when the tolerance f of x or absolute 1e negative 3. It's essentially the same question. I just copy pasted it, and let's see what it does. Everything looks right to me. Okay. Okay, so actually you'll see that what we did in the class we talked about is actually reflected in this code. Again, it also, it's nice that it writes all those comments and gives you how to run this. Now, it turns out that if you take this and copy paste, it will not work because this is not how you define a function in Octave. You need to separate out this part from there, and it doesn't really do that for you. So what I'm going to do is take this code, and I'll show you what needs to change. Open the editor, paste it. So when I save this, it's important that you save it as bisection method. So it'll actually prompt us to do that. Let me save it on, let's say just put it on the desktop. So call it that because the function is called bisection method. And then we can try running it. I don't know if it'll run. Change directory. Oh, it did run. Okay, that's good. So this is, I'm not really used to this method of writing code. It basically, what it does, it puts the function in the beginning, and then it puts the main block in the end. Now, it's interesting that the same code, when you run this, when I ran this on Mac, it did not work. Octave on Mac did not work. This is how, what I'm going to show you now is always guaranteed to work no matter what operating system. I usually take this part and I make a new file and save it with a different name. So let's call it main bisection. So there's a main file, which is like the driver which calls, and then there is the function which does the things for us. So if you run this, it told you the approximate solution is this, and then it told. So we can go through the code, but the point is I really want to know a few things, like I want to see how the solution changes, like, just like we did in the example. I also want to probably see how many iterations it took to solve. So what we can do is we can tell it to do that. So if you see this code, it says, let's go through it. So f of x is defined here. A and b is defined here. F of a, f of b, which comes from the computation. And then you can see that we have the bisection rule, and then it tests a termination condition. And then I told you that bracketing part, which is tackled over here, if else condition. What I don't like about this code is that I need to go and change f of x inside bisection, right? I don't want it. I want to make it an external function. I want to be able to define it here so I can put it as an input, because I want to make bisection method very generic. I can give any function, any solution, any initial guess. It should be able to work. So this, I'm not kind of happy with this. So I'm going to make it change the code. The function, the inputs to bisection method should be a function, initial guess, tolerance, and also add. So I don't have this condition of the maximum iteration. Add maximum iterations. Okay. So now you can see that if you see the function, it actually put in inputs f, a, b, tolerance max. That's how I would like to program it. And then a bunch of the code from here should be the same. I could, in fact, just modify some part of it, but let's just take this. So here you can see the usage. F is outside. And so what we'll do is we'll essentially replace our code with this new code. Okay, so here we go. Okay, and then I'll move this out because I want that in the driver, the main file. Okay, so here it told us it converged in 11 iterations, and the root is approximately 3.002. You can see it's accurate to 1 in -3. Okay, this is what we gave it. Now, as I said, we want to compare it with our solution here, see how the progress is made. So what we'll do is we'll ask it to add that part to the code. Please print the progress iteration. So this is actually this is just a print function, which it will probably put in the bisection method. Let's see if it does that. So everything here is the same, except that right here, fprintf, that would do the job which we're trying to make it do. So, okay, let's okay. What we could do is we could take the whole thing and copy paste it. That's one way to do it, but I think it's just that it modified this part. So let me just put that in the code, hoping that that's what it changed. But you could copy paste the entire code. So let's go to bisection. And I think it was put in just after c equals a plus b divided by 2. Okay. Okay, so let's go here, run this code. Okay, so it's not printing everything. Let's see what's wrong. CLC clear. Just printed the last iteration, iteration 10. This is a glitch in Octave. So it's supposed to run this while loop. And then, well, it's supposed to basically print this for every time while loop is executed. And this loop runs till iteration end. Yeah. So it's interesting that the same code I tried it on the Mac works fine. So how do we fix this? Could try this. Okay, so I'll try to fix this. So what we can do is maybe this will work. Okay. Let's save this. See if this code even runs. There's an error. Yeah, so what I was trying to do is basically try to take it row wise, stack it into a big string with each row corresponding to this line, and then print the string in one shot. Doesn't look like it's working. Wait, let me. Can we do? Yeah, I've noticed this glitch with the Windows version. Let's see if disp. Fprintf disp. Okay, so here is a different way of writing the same thing. Okay, let's see if this works. Same problem. It's clearing the screen. Okay, let's see if at least we can get it to print something. Yeah, so it's iteration 0, iteration 1. Well, that's not satisfactory, but at least it. Okay. Okay, that worked. So all I did was put a pause, so it just printed one by one. So we can now look at the. Oh my God, I lost that. What was? I lost iteration 1 through 5. To fix this display problem has been there. Is any of you face the same problem with Windows or a Mac? Not tried? No. Maybe there's a way to write it to a notepad before it quits. Maybe I can dig up the syntax for that, so that way at least it will be saved somewhere. Uh, uh, yeah, I can't think of any other better way. Uh, Okay, I'm going to quit here. So this is one. I just did Control C and it quit there. Maybe that's one way. So before it quits, you can quit it, but I'll work out a workaround to this, which will be basically you just write it to a file, like a notepad or a text file, and we read the text file. That way you can copy paste it to your homework or whatever. So anyway, so we were interested in figuring out the solution for 3 iterations. We did this calculation. If you remember, we were at 2.875 and 3.25. That was our third iteration. It's exactly that, right? So we stopped here, but you get the same thing with Octave. Now you might ask, this only gives you the solution between 1 and 4, right? How do you get the other one? Well, if you want the other solution, which is x equals 0, then you need to give it, you need to bracket that root. So maybe if you try -1 and 1, that brackets the root 0. So we could change this easily. So just make it -1 and 1. And I'm going to remove the pause because it's going to take some time. So let's go here. Remove the pause. Okay, so here it actually converges in 0 iterations because -1 + 1 divided by 2 is 0. So that was not a good one. So let's try 2. And then you can also try -10. Okay, so this is really far away. Okay, so that took 13 iterations, pretty fast. You could go 100 too. And so it took 15 iterations. So you see, when I went 100 to 2, it took 50 iterations. When I did 10 to, so it actually converges pretty fast, given that 100 is so far away, -100 is so far away compared to -10. What else? You could try this. Now we know that the root is between 0 and 3. So if you try to give values which does not bracket the root, it should return an error. So let's give 4 and 10. We know that 4 and 10 does not bracket the root, right? So good code will give you an error. So here is, so there's something which I cannot see here, but it should have code here. Okay, so it actually checks, this part of the code actually checks if f of a times f of b is greater than 0, that means you do not bracket the root. And if you don't bracket the root, should terminate. There's some problem printing it because of a bug in the Windows version, but it probably threw an error right there at line number 11.